Hello, this is Concrete Path. Today's lecture is about theories of failure. Different theories of failure. So the materials we have either ductile material or we can have brittle material. If we use that uniaxial loading, if we say the loading is uniaxial along one axis only, then we have a brittle. Let's talk about that ductile material. Let's say you have some bar, you are applying a tensile force, as that in case of a universal testing machine you are applying for the tension testing. So you are applying some stress sigma. So some sigma you are applying, and the material itself is ductile. The ductile material property of ductile material is that it has ultimate stress in compression greater than that yield stress in tension and greater than shear stress. So your ductile material is weak in shear. So critical for the ductile material is that it fails earlier in shear stress. So shear stress is critical for ductile material, and for the brittle material we say your sigma UC in the compression is greater than tau greater than sigma YT. That means it's weak in tension. So your brittle material fails earlier in at a stress that if you are applying a stress, say if you are applying a stress of 100 megapascal in tension, you are applying a 150 megapascal in shear stress, and you are applying 200 megapascal in compression. So on 200 megapascal it will fail in compression. If you are applying compressive forces on this material, it will fail at 200 megapascal. If you are applying 100 only in stress in tension, it will fail at a 10 sigma equals to 100. So that means it's critical in tension. This one ductile material is critical in shear stress. So if your material is ductile, let's talk about ductile material. So we have that we would say that the angle, yeah. Let's make the state of stress for this configuration of loading. So we would say sigma y is 0 and sigma x is equals to sigma. So this is your principal stress. Shear stress is 0 here. So if you want to say for the ductile material, your shear is critical. So shear, we know the shear makes tau max in plane. Yeah, tau max plane is at an angle of 45 from principal plane. So this is your principal plane. This is also principal plane. So at an angle of 45, you have to go at an angle of 45. So this is our 45 degrees from your principal plane or from vertical 45 degrees. Then you can get tau max plane. Yeah, this is our tau max plane, and the values would be some sort of value shear stress, some value of shear stress. So the material fails at an angle of 45. We can say shear stress, since material is ductile, it will fail in shear. So the shear plane, maximum shear plane, is at an angle of 45 from the long axis. So this is our long axis. So at an angle of 45, you have to go at an angle of 45, and material will fail in tension. So this is our 45. and this is 135. So the failure of this material would be in the form of, in this form. So this we call as cup and cone failure. For brittle material in tension testing. So this is making an angle of 45 degrees. This one is your 135. So we got this one, that for the ductile material, your failure in tension testing would be a cup and cone failure. Now if you say the material is brittle material, let's talk about brittle material. So material is brittle. You're applying the same stress sigma. So state of stress is that you have principal stress in plane P and Q. So we know that the shear stress plane would be at an angle of 45. So but the material is brittle. If the material is brittle, that means it's weak in tension. So tensile So tau, we can say material is brittle. That means critical is tensile stress. So critical is tensile stress, sigma tensile. So your tensile stress is along x-axis. That means that the plane on which that tensile stress acts is the vertical plane. So your vertical plane is critical. So this plane is vertical, critical plane. So it will fail in along that vertical plane. So failure would be in this fashion. So this is our failure, vertical failure. So 90 degrees with respect to long axis. So this is long axis. It's making angle of 90 degrees. Failure is making a failure angle is the 90 degrees with respect to long axis. Here the angle was 45 with the long axis. Now let's talk about that shaft. You have some shaft and you are applying torsion or torque. This is your torsional moment. We know that torsion induces shear stresses. So torsion induces shear stresses. That we have no stress here. We have no normal stress here. So only shear stress is on this plane. If you take any point and show the stresses, we can say this is some shear stress. There is only shear stress on this plane. So if the material is ductile now, ductile material is weak in shear. That means if the shear plane is making angle of 90 degrees along the long axis, though, that means shear stress is acting on the plane, this plane. So this is shear stress plane. That means the vertical plane is itself the shear stress plane. So this plane is the critical. That means the failure would be in this fashion. So this is our failure for the ductile material. But if the material is brittle, now if the material is brittle, that means brittle material. We know ductile is weak in tension, that shear, and brittle is weak in tension. So if the sigma we know that from shear stress plane, your maximum shear normal stress plane would be at an angle of 45. Do we know that this is your sigma 1? I can say this one is your sigma 1, that maximum normal strain plane, and this is sigma 2 compressive. And so it's making an angle of 45 from the shear stress plane. So if you go at an angle of 45 from vertical plane, this one is your vertical plane. That's also called as shear plane here. So vertical plane is the shear plane. So you go at an angle of 45 and you will receive a normal stress plane where the sigma is acting tensile. So at an angle of 45. So you go at an angle of 45. So this one. Similarly, you go 135 also. You go 135 also. Then the failure would be in this one, in this fashion. So this is failure. This is our normal stress plane, sigma 1 direction, or we can say sigma 1, sigma 2 direction. So these are the failures. These were all failures for material that we selected. So your failure, we can say your failure is a function of material and the loading. Is a function of material and loading. And we can also say that this all study was about the stresses in one direction only. So this is called as uniaxial loading. So we studied that failures in uniaxial loading. But in the real practice, we don't have the only one axial loading. We say that the loading can be that we say general state of loading, or we can say general state of stress. So that's why we can say your general state of stress. We are talking about general state of stress, that's multi-axial loading. So we can have from all other sides, then we can have this one. So we can have sigma x, sigma y, tau xy, sigma z. We can have tau xz, tau xy. We can have also tau xz. We can have tau yz also. So we have different combinations, that we have 9 combinations. So this is general state of stress. But till now we are focusing on in uniaxial loading, that we have only one state of stress, that we have one state, that directly we can say what is the failure, what should be the failure, how it should be the failure. But for the complex loading, it's critical that it is difficult to find that by which component of stress, which component stress contributes to failure more, which component contributes more to failure, and how much failure would be there. So we don't know. So for that we have different theories of failure, and that too are applied for different materials. So we have different theories of failure, different theories of failure. They do what thing? They compare general state of stress, that is multi-axial loading. They compare general state of stress, that's multi-axial loading with respect to that uniaxial loading. So they select a material and they perform uniaxial testing. Then after that, the results they compare them with the general state of stress they are having for the material on the real application. And so then after that we say you select a material M, and you select a different particular loading L. Then you say which theory would give you conservative results. So by selecting a material, say ductile or brittle, and loading, say any sort of loading, then we say which theory would give you best results, conservative results, such that your design is safe. Now we have different theories. So first theory is that major principal stress theory, that we call as major principal stress theory. That we call as, also we call it as Rankine theory. Rankine, or we can have Rankine or Lehm's theory. So they say that for no failure to happen, your major principal stress, that should be, this is major principal stress, that should be less than or equals to the stress that we have, yield stress in uniaxial loading. So we can write that. So they compare the stress, major principal stress, that has developed in multi-axial loading. That stress, major principal stress, that should be less than yield stress in uniaxial loading. So if we talk about pure shear case, let's say we talk about pure shear case. Let's say pure shear case. We have, for the pure shear case, we have sigma 2 equals to minus sigma, or tau. We can write in terms of tau. In terms of shear, we can write sigma 2 equals to minus tau, and sigma 1 equals to plus tau. So if you use that, and you write what's the maximum shear stress, that we can have tau should be less than or equal to sigma y. But it's not true. When you do shear test, when we do shear tests on ductile material, and we have some curve that gets developed, some sort of curve. Then so we say we have failure in shear, that's this is your tau failure. So tau failure is that means that your material fails in shear at a yield stress with some factor, that's √3. So that's equals to 0.57 Fy. That means that material fails at, if you perform shear test and materials, and you reach it to a stress value of say 0.57 Fy, the material will fail in shear. Material fails even on a shear stress value of 0.57 Fy, your material will fail. So if this method we are using for pure shear case, it is saying that you can allow tau allow can be less than or equal to sigma y. That means it's also allowing tau y equals to sigma y. That means it's not possible. It's not going to happen. As soon as you reach to 0.57 Fy, your material will yield. That means this method is not suitable for pure shear case. So you apply a cross here. That means it's not valid for pure shear case. So this is the strength that in the shear strength. That means the shear strength of material that ductile material is 0.7 Fy. So directly we can say it's not suitable for ductile material also. So ductile is not also suitable for here. If we say is it safe for brittle material? Is it safe for brittle material? We know that for brittle material, it's weak in tension. It's weak in tension. Your tensile stress is critical, and our sigma 1 is also in that tensile. So your material, that means it says that sigma 1 should be less than Fy or equal. That means this method is suitable for brittle material. This method is suitable for brittle material. So this method is suitable for brittle material because your brittle material is critical in tension, or we can say sigma normal stress. So this method is suitable for brittle material, not for ductile, not for pure shear. So this one is suitable for that brittle material. Then if we say for the design purpose, we apply a factor of safety also. We say for design purpose, your major principal stress that should be less than equal to Fy by that factor of safety. So we want to say your stress should not be more than Fy. If it is more than Fy, that means material will fail. So we also apply a factor of safety such that stresses are far below than yield stress. Next method is that maximum principal strain theory. Maximum principal strain theory. That's also known as Saint-Venant theory. So it says that for no failure, your major principal strain in multi-axial loading, that should be less than or equals to your strain in uniaxial testing, that's yield strain in uniaxial loading, So when we performed that test, we know that for the steel we had that some sort of that curve. So the yield stress was at that point B and D, then we call it as yield stress. So we say the yield stress was equals to, this was your yield stress, this was stress yield. So stress yield was, so yield stress was sigma y by E based on the Hooke's law, sigma y by E. So we write, and also for the multi-axial loading, we know that strain 1, major principal strain equals to sigma 1 minus mu sigma 2 plus sigma 3 by E. That should be less or equals to E yield, that's sigma y by E. So finally we can write that major principal strain theory says that sigma 1 minus mu sigma 2 plus sigma 3, that should be less than or equals to sigma y. And if you talk about pure shear, case, that means sigma 1 equals to tau, sigma 2 equals to minus tau. So if you substitute here, you write tau minus, and value for, let's write the value of mu equals 0.3 for steel, 0.3 into minus tau equals to, let's equate it with sigma y. So we get a value of 1.3. That means tau equals to sigma y by 1.3, that equals to 0.77 sigma yield. That means the value tau here, we can write it as tau LO. That means this method allows shear stress value of 0.77 sigma y. So this method allows a shear stress value of 0.77 sigma y, but material fails at 0.5 Fy. So this method is not suitable. That means pure shear you apply across here. So this is not suitable for ductile. It's not suitable for pure shear, not for ductile. So this is not suitable method for the pure shear and ductile material. If you want to say is it suitable for hydrostatic loading, let's talk about hydrostatic loading. If you write the equation that in the hydrostatic every sigma is same, if you write that, we can use that sigma minus 0.3 sigma plus sigma should be equal to less than or equal to sigma y. So if you calculate that, you got a value of 0.6, 0.4. That means sigma equals to 2.5. That means it allows us yield stress of 2.5 sigma y. That means it estimates it overestimates. It overestimates. That means it says that if the material yields at sigma y, you can allow 2.5 times that sigma y. That it overestimates the that ductile strength, or you can say yield strength of ductile material. Yield strength of ductile material. So it's not suitable for ductile material, not for hydrostatic. So next one is that third method that we have that major maximum principle, maximum shear stress theory, that we also call as Tresca or Guest or Coulomb. So shear stress theory says that tau max in the multi-axial should be less than or equal to tau max in uniaxial. So for the uniaxial, you have only sigma y is acting. Say sigma y is acting in one direction. So if we say what's the tau max for uniaxial, that is equals to sigma 1 minus sigma 2 by 2, that is sigma y by 2. So you're right, it should be less than or equal to sigma y by 2. And for the tau max in multi-axial loading, we have three possibilities. That tau max absolute, we're right, sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, and third one is your sigma 3 minus sigma 1 by 2. So maximum of these three, that's your tau max absolute. That should be less than or equal to tau max in axial loading. And if you are talking about that plane stress condition, then we can write. If you are talking about plane stress condition, then we can write sigma 1 minus sigma 2 by 2, comma sigma 1 by 2, and third one is your sigma 2 by 2 should be less than or equal to sigma y by 2. So if you say whether it is suitable for pure shear case, let's talk about pure shear case. For the pure shear case, tau, that sigma 1 equals to tau, sigma 2 equals to minus tau. That means if you write that tau, this one plane shear case, tau minus of minus tau by 2. This one we know that would be 0.5. So we write that should be less than or equal to sigma y by 2. So if you calculate that, you get a value of that tau should be equals to less or equals to 0.5 sigma y. That means it allows only a shear stress value less than 0.5 times sigma y yield. But we know that shear strength of material is tau. We know that shear strength of material equals to 0.57 Fy. That is Fy by root 3. So that strength is greater than the allowable stresses. That means this method is safe. So this is conservative. That means safe or conservative. So this method is best. We can say this is conservative method for ductile material. So it's best method if you say it gives conservative results. Not best, I would say it gives conservative results. That means it underestimates the strength. If the strength is 0.57, it says no, you keep the stresses below 0.5 also, not 0.51. You keep the stresses 0.5 less than 0.5 Fy. So it does not fully utilize the strength of the material. So it says that you don't use that 0.7 sigma y, the difference 0.07 sigma y. It says you use 0.5 sigma y and less than that. You don't use 0.57 Fy. So it underestimates that value 0.07. So we can say this gives conservative results for ductile material. That means we can use this method for this theory for ductile material, and for pure shear case also we can use this method. So if we talk about hydrostatic loading, hydrostatic loading. So for that you can have sigma max, tau max absolute. So we write for the hydrostatic, you have sigma 1 equals to sigma 2 equals to sigma 3 equals to sigma. So you write tau max absolute sigma 1, that means sigma 1 minus sigma 2 divided by 2, that is equals to 0. That equals to 0. So it says that tau max absolute equals to 0. That means tau max allowable equals to 0. So it's not a good sign that it says that you don't have to use any shear stress. So tau max is 0. That means it's not suitable for hydrostatic loading. Let's talk about fourth method that we call as maximum strain energy theory. Maximum strain energy theory. That we write as maximum strain energy theory, or we can write Beltrami-Higgs. So maximum strain energy, it says that maximum strain energy in multi-axial loading should be less than or equal to maximum strain energy in uniaxial loading. So this method uses only up to elastic limit. So you have that curve. So it says that this is our curve. It says that go to only elastic limit. Then we have that area, stress, strain. Then we write half of stress into strain. So it says that maximum strain energy, or we can say strain energy per unit volume. That called as modulus of resilience. It says that strain energy per unit volume in multi-axial loading, that should be less than or equal to strain energy per unit volume in uniaxial loading. So for the multi-axial loading, you can write half of sigma 1 E1 plus half of sigma 2 E2 plus half of sigma 3 E3. That should be less than or equal to, in the uniaxial loading, we only have that 1/2 sigma yield into E. This is the strain. This is strain 1, strain 2, strain 3. Strain along 3 principal directions. So then if you substitute that, we know that this value of strain equals to sigma 1 minus mu sigma 2 plus sigma 3 by E. Similarly, you can have E2, E3. You can also have that. So if you substitute those values in place of sigma 1, sigma 2, sigma 3, that in place of these 3, E1, E2, E3, then we can write the directly equation. We can get finally, we write that sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu sigma 1 sigma 2 minus 2 mu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. That should be less than or equal to Fy by, we directly say for design purpose you apply a factor of safety. For design purpose you apply a factor of safety, and you do a square of the both. You do square of both. So this is our conclusion from the results. This is the conclusion that this is for 3D case. This is for the 3D case, sigma 1 square. If you say for the 2D case, so for the 2D, if you write for 2D case, that means sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2. That should be less than or equal to, we can write sigma y by factor of safety whole square. So after that, next method is that we call it as yeah, before that we say that whether this method was suitable for pure shear. So we have studied it. We want to say whether it is suitable for pure shear case. For pure shear case, your sigma 1 equals to tau, sigma 2 equals to minus tau. If you substitute that, you write tau square plus minus tau whole square plus minus times mu. Let's use the value of mu equals to 0.3, then write tau into minus tau. and that should be less than or equal to sigma y square. So if you calculate that, that means tau allowable should be less than or equal to sigma y by, that means 0.62 sigma y. That means 0.62 sigma y. That means it says that you can allow shear stress value of 0.62 sigma y. That means it's not suitable for pure shear case. It's not, because it's saying that you can allow stress 0.62, but if the material reaches 0.57 Fy, it will fail in shear. So it's not suitable for pure shear case. Next method was your maximum shear strain energy. Maximum shear strain energy theory. So it says we also call it as distortion energy theory, or we also call it as Huber-Hanke-von Mises theory. So it says that maximum shear strain energy in multi-axial loading, that should be less than or equal to maximum shear strain energy in uniaxial loading, and after that we have a long derivation. We have a long derivation for the calculation of distortion energy. Then after that we reach a conclusion, a result that says that sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square, that should be less than or equals to sigma y by f of factor of safety whole square. Sigma y by f of factor of safety whole square. Then we reach to this conclusion. And for the 2D, when we say for the 2D, we write in terms of sigma 1 square plus sigma 2 square minus sigma 1 sigma 2, that should be less than or equals to sigma y by f of factor of safety whole square. So for the 2D case, you can see the difference between your maximum shear strain energy and that strain energy theory. That in that method also we had sigma 1 square, sigma 2 square, and after that there we have mu times sigma 1 sigma 2. But in this theory it says that you only have sigma 1 sigma 2, so there is no mu here. So this is the difference between the two for the 2D case. So if you say for the pure shear case, if we talk about pure shear case, so substitute the values that this is sigma square and this is minus sigma whole square, and this one is tau into tau minus tau. Then we write should be less than equals to sigma y, and you got a value of tau allowable. That means tau, the shear stress you can allow, that equals to sigma y by root 3, that equals to 0.57 Fy. So that means the conclusion is that your maximum shear strain energy theory is in perfect agreement, we can say, with pure shear case. So we can say for the pure shear case, only one method is applicable, that's perfectly applicable, that's called as maximum shear strain energy, and the one method was earlier that we call as maximum shear stress theory. Maximum shear stress theory says that tau allowable should be less than or equal to 0.5 F sigma y, and it was underestimating the strength of that ductile material. But this one, it's giving accurate results that the strength of that's equals to the strength of material in shear strength. So this is in perfect agreement with the pure shear case. So the conclusion of these methods, we also have one more method that we call as octahedral shear stress theory. The equation for this one in the 2D case, equation is that sigma 1 square plus sigma 2 square minus sigma 1 sigma 2, that should be less than equals to Fy by F of factor of safety whole square. So this is same as that of, in the 2D, equation is same as that of maximum shear strain energy theory, that the fifth one that we studied. So it is same for the 2D case, only for the 2D case. So from this one also we can get the values that for the pure shear, it is also in perfect agreement for the pure shear case. That means it will allow you tau LO, it would allow that sigma y by root 3. So this was one more method. That octahedral means we have octahedral planes. That means they are the planes. Octahedral planes are those planes which have equal inclination, which have equal inclination, which have equal inclination from all, we can say, three principal planes, all principal planes, from all principal planes. So these are the octahedral planes, or those planes which have equal inclination from principal planes. Then we can say for the 2D case that octahedral shear stress theory is same as that of maximum shear stress theory, shear strain energy theory. Yeah. So conclusion, we can say final conclusions. The conclusion we can draw from the theories that are important here, that we have conclusions. Say you want to use a theory that is suitable for brittle material. We'd say go for method 1, that we have maximum principal stress theory. And if I want to say I want to use method that's best for ductile material, I would say go for maximum shear strain energy theory. And after that you can have that octahedral theory, octahedral shear stress theory, octahedral shear stress theory. Then after that you can have maximum shear stress theory. Then after that you can have other methods also, that we have other methods, that is strain energy, that method 4, strain energy per unit volume. After that you have principal strain, that method 2. So here critical is that you have maximum shear strain energy theory, that's in perfect agreement with the ductile material, the pure shear case, Fy by root 3. This one also Fy by root 3, and this one is Fy by 2, that's 0.5 Fy. So for, if you say who is the most conservative method for if you say for the ductile material, most conservative method would be maximum shear stress theory. That maximum shear stress theory is the most conservative theory, that says that shear stress allowable should be less than or equals to 0.5 Fy. Other methods would say would give you shear stress more than the strength or equal to the strength. So this method gives you more conservative results. But if you want to design, you can say you can prefer this one also for the shear stresses also. So this is the end of the concepts behind those methods. So now if you want to take problem on the different methods, so if you want to say design the material for get the value of any particular value of stress, how much stress we can allow based on different methods we have. So based on these methods, how much stress they can allow for given configuration of state of stress. Let's say the state of stress is that we have, let's say the state of stress is that we have 1.5 sigma is its tensile, and we have here compressive minus 0.5 sigma, and on the top we have sigma positive tensile sigma. Then you have to say, based on the different methods, which method would give you tau LO, and which one would be among those, the tau allowable, the sigma allowable that is lesser, we will take that value, final value. So methods we have. Then also we need some data also. We say what's the value of mu and what's the value of E. The value of E you can take, value of E, let's forget for now. Let's take value of E as it's, let's take value of E as equals to E, value of mu equals to 0.3, and yield stress equals to 210 megapascal. You need to get tau allowable by using different theories. So let's say first method is your maximum principal stress theory, maximum principal stress theory, that says sigma max, sigma 1. Here the sigma 1, which one should be sigma 1? Is this sigma 1? So sigma 1 equals to 1.5 sigma. That should be less than or equal to, that should be less than or equal to sigma y. Can you say that? Can you say that? So that means sigma equals to, that means sigma should be less than or equal to 210 by 1.5. That is, that equals to 140, 155.55. So 155.55. That means sigma should be less than or equal to 155.55 megapascal. That means this allows a stress on the material, that means that is equals to this or less than this value. So if you use method 2, method 2, that says maximum principal strain theory, that means maximum principal strain value equals to sigma 1 minus mu sigma 2 plus sigma 3 by E. That should be less than or equal to Fy by E. That means sigma y by E. So you substitute the values. This value of sigma 1 we can use equals to 1.5 sigma, 1.5 sigma minus mu 0.3 sigma 2 minus 0.5 sigma plus sigma 3, we can say sigma positive sigma. That should be less than or equal to 210. So your sigma final value should be less than or equal to 155.55 megapascal. And that means in the first method you have a stress allowable that was equals to 140 megapascal, less than or equal to 140 megapascal. So this method allows 140, but the method 2 says let's allow 155 also. Now if you use third method, let's use the third method, that is maximum shear stress theory. Maximum shear stress theory, that says tau max absolute. The tau max absolute should be less than or equal to tau max in uniaxial loading, that's sigma y by 2. That means tau max absolute should be less than or equal to tau max uniaxial, that is sigma y by 2. So if you use that tau max absolute, so tau max absolute would be, if you take one value as positive, next one as negative, then you subtract them and you can get a value of, so if you take that one, we would prefer this value and the sigma 1. If we say 1 point sigma minus of minus 0.5 sigma by 2, this one would give more result. That is the maximum out of all those combinations. You would get this value as maximum 1.5 sigma minus of minus 0.5 sigma by 2. So that means sigma should be less than or equal to, value of sigma y was 210, so you can get a value sigma equals to 105 megapascal. Now if you use method 4, if you want to use method 4, so method 4 says maximum shear strain energy, maximum shear strain energy, maximum strain energy theory. It says that U per unit volume multi-axial should be less than U per unit volume uniaxial loading. So strain energy per unit volume, we have the result of that sigma 1 square plus sigma 2 square minus sigma 3 plus sigma 3 square minus 2 mu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. That should be equals to, that should be less than equal to Fy by Fy whole square. And you substitute the values, and I would say this is 1.5 sigma whole square plus 0.5 minus times 0.5 whole square plus sigma 3 was sigma square minus 2 into 0.3, then 1.5 into minus 0.5, then after that plus sigma 2 was minus 0.5, sigma 3 was sigma, and after that plus sigma 3 was sigma into sigma 1, 1.5 sigma. So that should be less than or equal to 210 whole square. So finally you get sigma should be less than or equal to 114.7 megapascal. Now if you use method 5, your method 5 says maximum shear strain energy theory. Maximum shear strain energy theory, the result for the direct results we have 1 by 2 sigma 1 square Yeah, sigma 1 minus sigma 2 whole square. Sigma 1 minus sigma 2 whole square plus similarly you have sigma 2 minus sigma 3 whole square. Sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square, and that should be less than equals to sigma y, that is 210, and finally sigma y whole square. And finally you get a value, you got a value of sigma equals to 116.487 megapascal. Now you got different results of the stress allowable stresses. So if you say which one gives the least value, or we can say conservative results. So from the method one, you got a value of stress 140. Then after that you got a value of 155, and after that you got a value of 105, and you got a value of 114, and you got a value of 116. And out of those, you can say 105 is the least value. 105 is the least value. So this method, we can say this is the conservative method for ductile material. So this is your conservative method, 105. Now next problem we can take. So next problem we can take. Let's have that. So we have provided you stresses. That means this one is your stress of 80. In the 2D, we can say this is plane stress condition. This is 80, shear stress 25, and sigma y equals to 60 megapascal. So 60. So you need to say you have mu equals to 0.3, value of E equals to 2.110 to the power 5 megapascal, and you have sigma y equals to 250 megapascal. Yield stress equals to 250 megapascal. You need to say by different methods get the value of factor of safety. So calculate the factor of safety using different methods. So for the method one, we can say that from the calculation we need firstly we need the value of principal stresses. We need the value of principal stresses. So sigma 1, 2, that equals to 80 plus 60 by 2 plus minus 80 minus 60 by 2 whole square plus 25 square, and you get a value of sigma 1 and sigma 2 96.92 and 43.07 megapascal. So we can say now for the method 1 maximum principal stress theory that says 96.92 should be less than or equal to 250 by factor of safety. That means factor of safety should be less than or equal to 2.57. So this one is sigma 1 should be less than or equal to sigma y by factor of safety. So we got a factor of safety less than 2.57. Next method we can write maximum principal strain. The principal strain maximum would be equals to E1 that equals to sigma 1 minus mu sigma 2 by E. That should be less than or equal to that sigma y by E. So we can say 96.92 minus 0.3 sigma 2 43.07. That should be less than or equal to your yield stress of 250. And for the design purposes, you have to get the factor of safety. So you divide the factor of safety here. So you have here factor of safety also divide by factor of safety. So you can calculate the factor of safety. That should be less than or equal to 2.97. Now if you are using for the third method, if you use third method, we can write method 3. That is maximum shear stress theory. We can write tau max. So tau max would be equals to sigma 1 minus sigma 2 by 2, or sigma 1 by 2, or sigma 2 by 2. So if you substitute, since both values are positive, if you subtract them, then the value would be, this won't be maximum, this won't be maximum. That means you take sigma 1 by 2, 96.92 by 2. This value should be less than or equal to, that tau max should be less than or equal to, tau max in multi-axial loading should be less than or equal to tau max in uniaxial loading. That's 210 by 2. That's sigma y by 2. Yeah, 250 by 2 megapascal. Sigma yield is your 250. So write Fy by 2 tau max uniaxial. Fy by 2. So, and you have some value of factor of safety also. And you have some factor of safety also. Factor of safety. So you get a factor of safety less than or equal to 2.57. Similarly, if you use method 4, method 4 says maximum strain energy theory. Maximum strain energy theory says that sigma 1 square plus sigma 2 square minus mu sigma 1 sigma 2, or 2 mu, yeah, minus 2 mu sigma 1 sigma 2 should be less than or equal to Fy by factor of safety whole square. This is the result for this one. Fy by factor of safety whole square. So you have the values of sigma 1 and sigma 2. So you write 96.92 whole square plus 43.07 whole square minus 2, 0.3, 96.92 and 43.07. That should be less than or equal to 250 square by factor of safety whole square. That means factor of safety would be equals to 2.67, less than or equal to 2.67. Then after that, if you use method 5, method 5 says maximum shear strain energy theory. So it gives you a result that sigma 1 square plus sigma 2 square minus sigma 1 sigma 2, that should be less than or equal to 250 square by a factor of safety whole square. So you got a factor of safety equals to 2.97. Factor of safety equals to 2.97. So this problem was related to plane stress condition. That means sigma 3 was 0. So plane stress condition. Then we got different values of factor of safety. So this is the end of that stress transformation problems and the chapter itself. So next chapter would be dealing with bending stresses. Thank you for watching. See you soon. Yeah, see you soon.